Welcome back. So today is lecture 20 and today is the last lecture for gallium arsenide MESFET, microwave MESFETs. Okay, and although some of the concepts that we discussed today are readily applicable to HEMTs going ahead, but we shall discuss them in the section of MESFETs nonetheless. Okay, so over to the whiteboard here. You can recall that in the last lecture 19 we had ended the talk or discussion on the requirements of a field effect transistor for making a good power amplifier. Again, power amplifier is one of the most important blocks of for instance the front end module of a cell phone, or if a TR module, where especially when you have a battery operated gadget, power amplifier it takes a special importance because it is the most power hungry block on the RF chain. And of course there are many different components of RF circuit or engineering, and gallium arsenide is useful for other applications also as a mixer, oscillator, LNA, etc. But we are starting with how it is what are the device requirements for making a good power amplifier, and whatever we had listed here are also applicable to gallium arsenide HEMTs, gallium nitride HEMTs, etc. Okay, so this is not just for gallium arsenide MESFET, but we know that for good power we need to have good breakdown, good current, good thermal management. If you cannot dissipate the heat away well, your device performance will suffer. Current collapse, we will come to that subsequently in one of the lectures. Essentially what it means is that whatever current you get in a DC measurement is not the same current that you might get when you pulse the or when you subject the device to kind of an RF kind of a situation where the current might collapse because of the effect of traps. We also need good gain. And that directly relates to a good transconductance. So you need to have good channel confinement, short gate length, good back barrier, good control of the gate on the channel, etc. And efficiency is a more complicated term. It has a lot of factors coming in there. You should have high gain, but also the biasing conditions and the device geometry, etc. also plays a role. Okay, and we concluded the discussion by saying that at whatever frequency you want to deliver power from a power amplifier, the cutoff frequency should be a few times higher than that in order to get reasonable gain. Sometimes the gain may not be an important parameter, in which case you can have a cutoff frequency which is just 2 or 3 times more. Okay, but if your gain requirement is also there, then you better have a cutoff frequency which is higher. Okay, but not super high, because then you will have to sacrifice on the breakdown. So those trade offs keep coming in there. So now going ahead, one of the most important thing in power transistor, when I say power I mean power microwave transistor, which are used as in a power amplifier, is heat management. How do you dissipate the heat away? Okay, because your device will heat up when you have sufficiently high RF power. It can heat up to much higher temperature, 150 degrees Celsius for instance, even 200 degrees Celsius if you are looking at really high power. So how do you dissipate the heat away is a very important question. So in gallium arsenide transistors, and this is applicable to HEMTs also, by the way, which we are going to discuss next in the next week. In gallium arsenide what you do is that you have to thin the wafer. What is meant by thinning the wafer? Maybe I will choose a different color here. Okay, the wafer has to be thinned, which means your wafer, if you take a wafer, it is of a certain thickness. Okay, but gallium arsenide has a poor thermal conductivity, which means whatever devices you have on top, they will not dissipate the heat below properly, because you need to have a heat sink below to take the heat. The heat sink is typically a metal alloy, like a copper molybdenum alloy for instance. It could be a copper molybdenum alloy. It is like a block, it is like a rectangular cuboid slab on which you have to attach the die so that the heat can be taken away. This is copper moly block for instance. Okay, but the gallium arsenide wafer thickness provides a thermal resistance part, so you need to thin the wafer. So people use techniques like grinding, lapping. These are different techniques by which your gallium arsenide wafer is thinned down. Okay, you have to be very careful while thinning. You should not crack or break the wafer, but it is typically thinned down to something like say 100 micron, could be less than that also. Okay, around 50 micron, depends on the technology, 50 to 125 micron. It will be thinned down to something like that, and then it will be put on a heat sink. So in this image you can see that these are the transistors on top, source, gate, drain for instance. There could be many transistors, of course there will be many fingers also for higher current densities, and you can see that this is your heat sink, which is your copper moly for instance, and you have thinned, this is a thinned gallium arsenide substrate. You thin it down so that you can reduce the thermal resistance part, which means your heat can be taken away more efficiently because you have a thin resistance in the path, thermal resistance. Okay. So, that way you thin the substrate and then you attach it and then attach it to a heat sink essentially, okay, and the heat sink will take the heat away here. Now, you can also see that this gallium arsenide wafer has a hole here and the metal is going all the way up, you know, to the source pad here. This is a source. You can see that the source, maybe I will remove the annotations here. You can see that actually the wafer, you know, if I take a cross section of the wafer like that, you pattern it and then you drill hole here. You drill hole here such that the wafer will look something like this now. Okay, you drill hole. These holes are of small dimension. You drill all the way till the top until you see the source pad. Okay, until you see the source pad. So, this is your source pad. This is your source pad, drain could be here, gate could be there. Okay. So, this is your source pad. So, you can say the source metal, you drill the hole in the gallium arsenide substrate so that you expose the source metal from the back side, then you fill it up with metal, and this metal is for instance it could be nickel. You can do electroplating of nickel, okay, and you have to use some kind of a mask to etch 100 micron or, you know, such high thicknesses. You need to use some kind of a nickel or some other mask when you expose the wafer to DRI, deep reactive ion etching. That is a high power plasma etching tool where you have to put the wafer such that the high power plasma like a fluorine plasma or something appropriate plasma will essentially etch the entire wafer in that particular hole to the back side of the, until you reach the back side of the source pad there, okay, and you use a mask to etch that, of course, otherwise the whole wafer will get etched. You do not want that. And then you fill it up with some kind of a metal like a copper or nickel electroplating, and then you short the source from the backside. So, what happens is that there is a metallic backside plane. It is a metallic backside plane. It helps in providing a ground plane. It is a ground inductance plane. The ground inductance plane helps in many ways. For instance, it can also take the heat away from the source because it is directly there, which is a better way also apart from the heat sink. Secondly, it provides a global like a ground plane on the back side to which you are connecting or short circuiting the top source. So, the ground on the top and the ground on the bottom is the same ground. Otherwise, what happens is that sometimes you may have two different levels of ground on the top and bottom, and that is not good thing because you will have significant RF losses. If the backside is not the same ground, your devices on the top will couple capacitively to the backside and you will have a lot of loss. So, you could have a lot of loss. So, you need to have a ground inductance plane that ensures that the top and bottom are at the same ground, okay, level, and most importantly your inductances L, the inductances actually come down, especially for high frequency circuits or for high power really large periphery devices. What happens is that we will come to multi-finger devices in another lecture when we talk about maybe gallium nitride HEMT. We will talk in more details about multi-finger HEMT and the power cell combination, etc. But in a real high power RF device for power amplifier, you will have many fingers, you will have many gate manifolds. So, the thing is you need to wire bond those source pads to the outside package, for instance, you know, on a board, on evaluation board or some kind of amplifier board. Those wires are okay as long as you are in a low frequency like 1 or few gigahertz, but if you go to higher frequencies, then the inductances can be really high and that can really kill your RF performance. So, the source being metallically shorted to the ground plane provides a very low inductance path, and so it reduces the overall inductance, the source inductance, and that helps in your high frequency power performance. So, this is an important function of the ground via hole. In another approach for heat management, and this ground via hole is not only for heat management but for ground inductance plane also. However, the metal heat sink here, the copper moly heat sink is for purely for heat management. Another approach that they do is that they flip chip, which means they invert or they flip the wafer upside down. So, this wafer is a flip chip, it means it is inverted upside down. You see, this is the back side of the wafer actually, this is the back side of the wafer, and you are flipping it, and then you are using there is something called flip chip bonder, you basically bond it to the metal heat sink directly. Now, what is the advantage? The advantage is that your heat is generated on the top actually, in the gate drain region or the source drain region is where you are generating the heat, and because you are taking the heat down here, it has to cover a large distance of say 100 micron of gallium arsenide with a very poor thermal conductivity, which is not the best of scenarios. So, if you flip chip and put it upside down, then your heat generating point, which are also called hotspots, are relatively much closer to the heat sink, because it is only defined by the thickness of this bonding material, which could be say the source pad could be say 20 micron thick, okay, and it is bonded die bonded upside down. So, which means your metal heat sink and your source drain could be only 20-25 micron away, okay, and this is the bonding material will be there, could be dielectric passivation also could be there. So then it takes the heat away more efficiently as compared to the situation where the heat has to travel like 100 micron or 50 micron below, okay. So this is an interesting aspect also. And the final thing is that you have a heat sink, of course, and you may or may not have a source via, this is called a via, the via hole, or people also call it TSV, true substrate via. You may or may not have a true substrate via, which here in this case the true substrate via is not shown, but you have something called air bridge where the source and source pads are connected over a bridge, okay, and they bypass the gate drain in between, and in between there is air because you want to minimize the dielectric constant, and air has the lowest dielectric constant because the lower dielectric constant will give you lower capacitances, which is good for reducing RC delay. So you need to have just air, it is called air bridge because it is filled with air only, it is just like air, but the bridge should not collapse. So this process development is also not trivial, it needs a lot of effort and careful optimization to come up with a structure like that. Essentially you have many structures, and we will come to this when you talk about gallium nitride HEMT, of course. This is suppose source, this is drain, this is source, this is drain, and this may continue for a long number of times because you need to have very large periphery of the device to carry very high current, and gate might be in between, okay. So you have to connect the source, this source to that source, this source to that source, and so on and so forth, okay. So that is what precisely the air bridge does. Air bridge helps connect the sources, it is not necessarily for heat management, okay, but you can actually fill this here inside of this with a highly thermally conducting or a heat sinking material at the cost of reduced frequency performance, but for lower frequency like 1 gigahertz or something you may not be so much concerned. So people also propose or have demonstrated that you can fill this with high thermal conducting material, and then on top of that you have the bridge. In that case you do not call it air bridge, but it can take the heat away more efficiently, and if you leave it with air, it is called air bridge, and air bridge is a very important technique for shorting the sources. Even in the presence of air bridge, it is a good idea to have the source connected from the back side for a source ground inductance plane and for taking the heat away better with the heat sink attached to the bottom, okay. So this heat sink is there, of course, and whenever you package the device, and this is not packaged, this is just the bare die, but when you package the device also the heat management is a very important problem, how the package flange is mounted on a die, for instance, on this kind of a heat sink. People also have academically and otherwise bonded it to a diamond because diamond has one of the highest heat thermal conductivity, so diamond can dissipate the heat much better. People also use liquid cooling where they bring in liquid at the back side of the wafer to cool, and that is the most efficient form of cooling, but it is more of a hassle to bring in liquid and take it out, etc. It is not very compact, but those are the things that people have done to show that your RF power performance in terms of watt that you can get, how much watt or kilowatt you get, can be significantly boosted with much better heat management. So heat management is a very crucial necessity or a technology in power HEMTs, okay, not necessarily for mixers or low noise amplifiers, but for power amplifier FETs, transistors, it is a very important approach or technique, okay. Now as we talked about in the slide before that we need a good thermal management, and we also need a high breakdown and high current. High current will come from multi-finger device that we are going to postpone to another discussion, but high, because it is the same discussion by the way. High breakdown, to get high breakdown, as I told you, people have used gate recess. You can see here in a MESFET, for instance, if you just have a planar MESFET where there is no recess and there may be no N plus layer also, the weak point comes here, the shaded region here tells you the point which is easily broken, the drain edge here might easily break, okay, if there is a dope layer below it, for instance. Even whenever you have a dope layer below the drain, people have found out whenever the nominally doped channel meets the highly doped region, that region has the weakest point where the avalanche will initiate first, or which will break down the first, okay. If you have a recess gate, for instance, the drain edge of the gate, which is this edge, the edge of the gate metal that is facing towards the drain, at the point below that is the weakest point, okay. That point will break down first, or the avalanche, essentially this point will have the highest electric field, and as you keep increasing the drain voltage, eventually you will reach a field which is critical field, and you will start avalanching or impact ionization, and you result in a breakdown of the device, okay. If you have a recess structure, okay, and in this particular structure there are 2 points, one point is this, one point is this. This is the point below the drain, okay, where also you might have a very high electric field because of the the way the field is distributed. So these are the things that you should keep in mind, that these are the points where the electric field is going to be maximum, and is there a way to reduce the the electric field. That is why the gate recess was a technology, and field plate also. We will talk about field plate when we discuss about AlGas GaAs HEMTs in the next week's lecture, but both for gate recess as well as field plate, you are able to improve the breakdown. In gate recess, however, the gate leakage should not increase, that is a very important mandate. Okay, if the gate leakage starts increasing, then your breakdown will happen early because of the increase in the gate leakage. Okay, so this is a more blown up image of a gate recess. So you can see this is the gate which you are putting on a recess. This is your recess spacing. You mean to say what is the distance from the gate metal to the recess edge. Okay, this is your LR, and you see this part, this white part, this is the surface depletion. That means you assume that some part of surface is depleted because of the way the material is, surface spinning. This is also some kind of surface depletion. You can see there is some surface depletion. This is your total thickness of the N plus layer, for instance, or maybe the N plus cap the channel to some extent, and this is your A is actually the channel. This is purely the channel here. So most of the electric field lines that originate from the depletion region will terminate in the gate metal actually this way. So that is why this part is the most crucial part which breaks down earlier. Okay, so people have simulated and shown that if you assume that there is a surface depletion from the top, then your breakdown is actually high with respect. This is on the x axis, you have LR, the recess length, this. If your recess length is this length, the spacing between the gate metal edge and the edge of the recess, if that spacing increases from 0.2, 0.4, 0.6 etc. up to 1.2 micron, your breakdown voltage also keeps increasing. Okay, not exactly linearly, but it keeps increasing provided there is a depletion from the surface. If there is no depletion from the surface, then this will put a limit. You cannot increase beyond a certain point. Your breakdown voltage will be fixed, does not matter how much is your spacing between the gate metal edge and the recess edge. Okay, so you can imagine this recess, this is the LR basically, this is your LR. So the more further you keep the LR, the more higher breakdown you get, but at the cost of higher drain resistance, drain excess resistance RD, which will basically reduce your cutoff frequency FT and Fmax, but that is okay. You have to always sacrifice a little bit of cutoff frequency for higher breakdown. So without depletion, surface depletion, you will have a lower breakdown and it will saturate with the recess length. With surface depletion, your breakdown will keep increasing. Experimentally, people have found it somewhere in between, but it is closer to the scenario where there is a surface depletion. This indicates that there is most likely a surface depletion from the top. Okay. Now this is a very important point that we are coming to this in this slide, which is called the power RF power figure of merit. We also call it the Johnson figure of merit for high frequency power transistor. What it says is that the product of the cutoff frequency and the breakdown voltage is constant for a given material, and it depends on two material parameter. One of them is velocity of saturation, which is fixed for a material. One of them is critical breakdown field, which is also fixed for a material. It weakly depends on doping, but we can ignore that. Okay. So the product of the cutoff frequency and the breakdown voltage is constant for a given material, which means if you plot the breakdown voltage on the y axis and the cutoff frequency Ft on the x axis, you are going to get a plot like this, because with higher cutoff frequency you are going to, it is like x into y equal to constant. So if you are plotting x and y, then you get a plot like this, okay, in log scale. It is a log scale. So you get with increasing cutoff frequency, you have a lowering breakdown voltage. It is the trade off that we talk about, which means for a higher speed device your breakdown will be low, and for higher breakdown device your speed will be low. So it is a trade off, and it is a product of the now the critical electric field Emax, for instance, for silicon is say 0.3 megavolt per centimeter. It is a material property. Velocity of saturation is also around 2 into 10 to the power 7 centimeter per second. Now if I take those values, then silicon gives you this point, but germanium gives you a lower curve here. Gallium arsenide, we are talking about gallium arsenide MESFETs, gallium arsenide HEMS, does not matter, it is here. Okay, this is actually gallium nitride, this, or this is silicon carbide, this will be gallium nitride, will be somewhere here probably. Okay. So what it tells you is that the further the curve is here, it means it has a better Johnson figure of merit, which means the device or the material technology is more suitable for RF power amplifier. So you can see that if I take gallium arsenide, okay, if I take gallium arsenide, maybe I will take a blue color here. So if I take gallium arsenide here as opposed to silicon, then for a, say I want to have a cutoff frequency of 10 gigahertz here. You see, for a cutoff frequency of 10 gigahertz, silicon will have probably, I do not know, 30 volt or something as a breakdown, but gallium arsenide will probably have 80 volt of breakdown. Okay, and gallium nitride will probably have more than kilovolt of breakdown, for everything remaining the same. This is because the critical field of gallium nitride, for instance, is 10 times higher, which is 3 megavolt per centimeter, while the velocity of saturation is almost 2 into 10 to the power 7 as the same as silicon. So what it means is that gallium nitride will be 10 times better than silicon here. Diamond is the best, but diamond has many technological issues. I am not going to that right now here, but you can see that indium phosphide then is better than gallium arsenide, silicon carbide is better than indium phosphide, gallium nitride is better than everything else except diamond, for instance. Okay. So, this Johnson figure of merit tells you how suitable a material is. We can see that gallium arsenide any day is better than silicon for a given frequency, for a given breakdown voltage. In other words, for a given frequency you will get a higher breakdown voltage at gallium arsenide compared to silicon and vice versa. Okay. For a given breakdown voltage you will get a higher cutoff frequency for gallium arsenide as opposed to silicon, and this relationship is derived in a very easy way actually. It is very easy. If you take just any piece of semiconductor here, say n-type any semiconductor, and if you consider this n-type semiconductor, this could be the gate drain region, this could be the gate drain region in FET, which means this is your gate, this is your drain. So, all the electric field or the voltage is blocked between the gate and the drain region, as I keep mentioning, and of course the electric field profile is not linear, it is non-linear, but for the sake of simplicity assume that the electric field profile is linear and the maximum electric field that you can sustain is your, it says Emax. Emax is the maximum electric field that you can sustain. Ideally the maximum electric field happens only here, not everywhere else, but let us assume that maximum electric field is everywhere, which is the best case scenario. Then, and if this is length is L, then the product of the maximum electric field into the length is actually your breakdown voltage, but this is an overestimate. As I keep telling, the electric, essentially if you plot the electric field, just electric field versus the distance, then the electric field whatever distance it has, the area under the field and distance is your breakdown, is your voltage actually, the voltage you are dropping. Okay. So, if this hits the maximum point, then this entire is the breakdown voltage. Now, if this is a peak electric field at only one point, rest of the portion the field is not peak, but this point will break down sooner and the device will break down. Now, if you assume that the electric field is everywhere the same, then you have a rectangle like that. You see my point, because everywhere the electric field is maximum. So, in that case you have a rectangle which is twice the area of the triangle. So, your the breakdown field, the breakdown voltage, you will get 2 times the breakdown voltage for a rectangular shaped electric field profile as opposed to a triangular shaped electric profile, but in reality the field profile is more like a triangle, not like a rectangle. So, this product which is a rectangular product is actually an overestimate on the breakdown voltage. Okay, it is an overestimate on the breakdown voltage, but nevertheless the breakdown voltage is given by this. Okay, if your breakdown voltage is given by that, then your if that is your breakdown voltage, now the cutoff frequency, you can say the cutoff frequency, you can say it is 1 by 2 times 2 pi times the time the electron takes to travel from this point A to this point B. Now, the time that electron will take to travel 1 by 2 pi is basically the length L divided by the velocity of saturation, because the electrons cannot go faster than the velocity of saturation. Actually, it should be 2 times the velocity of saturation, because this is a space charge region. Space charge region means this is a depleted region. Okay, only in depleted region it will block the voltage, it cannot block the voltage when it is not depleted. So, when it is depleted it is a space charge region, you can say, in any semiconductor, and space charge transport has a factor of 2 here, that is a different derivation by the way. So, essentially your cutoff frequency can be expressed as Vsat divided by pi times L. Okay, that is your cutoff frequency. Now, L you can see from here, L is nothing but the breakdown voltage into the critical electric field, correct. So, I can put this as L. So, if I put that as L, here, what will happen is that this is a cutoff frequency by the way, correct, Ft. So, if I put that as L here, then Ft will be equal to Vsat pi times this Vbr divided by Emax. You take the Vbr the other side, Vbr into Ft is equal to Emax Vsat by pi is precisely this relation. Okay. So, essentially this is a best case scenario and this is overestimate. So, do not think that this is you cannot break this limit, this is the theoretical maximum limit. Okay. But this is an important figure of merit to understand as we talk about RF power devices. Okay. Maybe I have to remove the annotation, otherwise you cannot see it here. These are some data from taken from this source on DARPA, defense, it is a defense agency in the USA. You can see that of course gallium nitride has better than indium phosphide than silicon, but these are experimental data points from different kind of technologies. This is gallium nitride HEMTs, those are gallium arsenide, there is silicon carbide MESFET here actually, whereas silicon carbide MESFET is here, indium phosphide, indium gallium arsenide HEMTs are all here. We will talk about HEMTs and pseudomorphic HEMTs in subsequent weeks. So, then we can come back to this image, but anyways gallium nitride has far better power performance for a given frequency, whereas if you are talking about hundreds of gigahertz, indium phosphide HAMT, gallium arsenide pseudomorphic HAMT, those are the contemporary technologies that are being used, because gallium nitride is not yet mature enough to be commercially used for few hundred gigahertz. If you want to have power at 100 gigahertz, that research is still going on gallium nitride. But for millimeter wave, even for 30 gigahertz, 40 gigahertz, etc., not to speak of traditional microwave, gallium nitride is much more power. It gives much more power than indium phosphide or other technologies. Okay. The other thing that we have to talk about when we are talking about power amplifier, a transistor for power amplifier, is the maximum output power that you can get from a power transistor, an RF transistor, that is given by 1/8 times the maximum current density times the maximum voltage minus the minimum voltage. Now, what is the maximum versus minimum voltage? You see, this is your IV characteristics, this is your minimum voltage, this is called the V minimum or the minimum voltage. Why? Because you would not want the output drain. You see, this is the output drain swing. In an RF voltage, in an RF operation, when you bring the RF signal to the gate, at the output drain you are going to get a drain voltage swing like this, correct? You are going to get an output drain voltage swing like that, right. So, this swing can happen between, this is the breakdown voltage, it cannot go above the breakdown voltage, otherwise the device will break down, and it should not go below the knee voltage, otherwise the gain will significantly drop, because the linear region is of no use, this region is of no use. Okay. You only use this saturation region, this is your saturation region, only there you can get the gain, and of course the output slope or the conductance should be as low as possible. Okay. So, your swing is limited by the maximum breakdown voltage minus the knee voltage, which is what precisely here I am saying V max minus V knee. Okay. That is the maximum voltage swing you will have. However, you will bias it at the midpoint of that. Okay. You have to bias it at the midpoint of that, so that the swing goes equally on both sides. You cannot cross the breakdown voltage, you cannot go lower than the knee voltage. So, that is why you have half of V breakdown minus V knee. Okay. That is the thing. On the output side, you have a maximum current, this is your maximum current, the current will swing between the maximum current and 0, it cannot go beyond that. If you go above the maximum current, the gate will leak and the gate drain diode will turn on and stuff like that. So, there is a maximum current that you will get, which is your Imax, okay, the maximum current you will get. So, this maximum current is Imax, so you have to put it as a midpoint of that for the max, the swing, you do not necessarily have to put at midpoint, you can have at a lower bias also different classes, class B, class C, etc. will come, but the best case scenario is that for output power is that middle, you are biasing at the middle point, which means there is a half into the maximum current you can get. Okay. So, the power, this actually is given by, because you are time averaging this, you are time averaging this sine wave, so there is a 1/√2 factor for both. So, essentially it is half 1/√2 into 1/√2 into half of V breakdown minus V knee into half of I max. This gives you 1/8 into the maximum current into the breakdown voltage minus V knee or V maximum minus. So, this is your maximum power you can get from a given material, from a given device at some frequency. The frequency is not specified here, but with higher frequency this will only come down. Okay. So, that is why your breakdown voltage has to be very high, your knee voltage has to be very low, your current density has to be high, then your output power is going to be high for a particular RF power transistor. Now, again, if I assume a linearly dropping field and across the depletion region, then the product of the breakdown voltage into the length, which is an overestimate by the way, is your voltage, the breakdown voltage minus knee voltage approximately. So, the length of the area can be put, the channel can be put as velocity times time, velocity times time is the length. Okay. So, if you do that, then you get something like this. This is basically the same relation that we are talking about, this is power by the way. So, there is a power which is inversely proportional to the frequency. However, in reality when you have multiple sources and multiple drains for an actual device, you will see that there is a gate here, the gate feeds everywhere, right. Now, what happens in RF is that it is a distributed network, and as the RF signal propagates, there is something called dephasing, which means the phase coherence need not be necessarily maintained when your device dimensions are big. So, the remote part of the device, the far away part of the device will have out of phase waves as compared to the part of the gate which is directly feeding in the input signal. So, you are bringing the input signal here and this is distributing across the manifold. So, the point where you are bringing the RF in signal, at that point your phase coherence will be lower, decoherence will be lower, almost none, but as you are going to the far away corners of the device, your phase of the RF wave will start becoming decoherent, they will become out of phase, and so that will deliver lower power to the drain and your power performance will significantly suffer. Okay, this is your phase delay will come. That is why you need to consider an additional 1/f factor to ensure that the RF waves are not dephasing, which means your device dimension needs to have the another factor of 1/f scaling. That is why the power does not scale it 1/f, but it scales by 1/f square, because there is an additional 1/f factor because of dephasing. Okay, you need to scale down the device dimension, I mean to say the width. This width of the source and drain has to be scaled according to the frequency. So what I mean is that if you have a certain gate, I mean source and drain, suppose this width of the channel, suppose it is certain width for say 1 gigahertz transistor. For 10 gigahertz or 20 gigahertz transistor, when I say 10 gigahertz 20 gigahertz, I mean power at 10 gigahertz or power at 20 gigahertz, then you cannot maintain the same width, you have to decrease the width by 10 times or 20 times, only then you will get the same kind of output power density, which means there is an additional 1/f factor, and that is why you have PF square law, which means the power times the frequency squared is going to be constant. And here of course, as you can, I will remove this annotation so that you can see it better. Here you can see that there is an output current swing of course, and then there is an output voltage swing, but you have to bias it at certain point. So if you are biasing it at point, the current, the device will exhibit this load line, the current can change across this load line. This is called the load line, right, the load line. All of you know that from your undergrad courses, I am sure. The slope of this load line, or 1 by slope of this load line, is the load, the resistance across which you are delivering the power. And you can see that the load line has this negative slope, which means when you go to the higher current, your voltage is minimum, and when you go to the higher breakdown voltage, your current drops to minimum. So your current, if it is like that, then your voltage will basically have the opposite behavior, which will go like that. Okay, the current and voltage are 180 degree out of phase because of this reason, 180 degree out of phase. Okay, and this is the load line across which you are delivering the power. Now you need not bias here, you can bias it here also, in which case the output, the current will not be able to swing completely. For instance, you are putting at the midpoint, that is why the current can go half above, half down, but if your current is suppose 1 amp and 0 is 0, so you are biasing at 0.5 amp so that it can swing across this. Okay, but if you bias it at say at this point where it says 0.1 amp, which means on the bottom side the waveform will be clipped, it cannot go below 0, right. So those are different classes of biasing, you call them classes of biasing. We will come that again later towards the end of this course when we talk about these classes of power amplifier, but those how you bias the device significantly matters for your efficiency, for instance. Okay, so that brings me to the last part of the power amplifier transistor here, which is that these images are taken from a thesis of Dr. Sai Charan, who was a student at ISC, but nevertheless it more or less looks similar for even any other transistor. This is for gallium nitride, but for gallium arsenide MESFET, gallium arsenide HAMT, the main concept is similar. Okay, so there are three very important things. One is gain. Of course, gain is how much output power you are getting in RF divided by how much input power you are putting in RF, and this is expressed in dB. So it is a 10 log of this power output by power input as a base of 10, and you express it in dB. Okay, that is your gain. So in these images, this is your gain, this is your gain. So you can see, and this axis is the gain. So you can see gain is around 10 dB, and 10 dB it stays constant, then it drops at higher. This is your input power, and this is your gain, for instance. So the gain drops. Okay, this plot is at a drain bias of 6 volt, you have to bias the drain, no, this is at a drain bias of 8 volt, this is at a drain bias of 10 volt. You can see that output power keeps increasing from 1.44 watt per mm to 2.14 watt per mm, 2.75 watt per mm. With higher drain bias, your output power also will, the maximum output power will also increase, but you can see that the gain with, okay, that is with different drain bias. Now x axis is always input power, and input power is expressed as a dBm. Do you know what dBm is? dBm is basically 10 into, it is basically 10 log of to the base 10 how much power you are getting with respect to 1 milliwatt, 1 milliwatt. Okay, so essentially if I say this is your 10 dBm of input power, so if I say 10 dBm of input power, it means I have to divide by 10, which is 1, and then I take 10 to the power 1, which is 10 into 1 milliwatt, so it is 10 milliwatt. So 10 milliwatt of input power, 10 milliwatt of input power is 10 dBm. Similarly 20 dBm will be 100 milliwatt, 30 dBm will be 1 watt, etc., etc. Okay, so this is your concept of dBm. Alright, and this is your input power, by the way, this is your input power here. Okay. And you can see that the gain is around 10 dB, it stays constant, then it drops. That is the typical behavior gain will express, gain exhibits. Again, gain is around 10, 11 dB, it drops, gain is around 10 and again it drops. The higher dropping that happens at higher input power is called gain compression. The gain compresses, okay, the gain will compress at higher power, that is a nonlinearity that kicks in. Okay, that is a nonlinearity that kicks in. Alright, this is your output power, you can see this is output power increases as long as the gain is flat, the output power is also linearly varying, and then as the gain drops the power saturates, it is the same thing. So it is this value is for the saturated power only, this value is for the saturated power, okay, that is the output power, the RF output power that you, and the way you measure all of this is on the wafer. If you want to measure this, then you use a equipment called the load pull. Okay, maybe we will again come to this at the end of this course when we discuss about RF and microwave concepts in a way, but load pull is the instrument where you use to measure on wafer RF power. Okay. And finally what we talk about is power added efficiency. It is one of the most important parameters, especially for those RF systems which are operated by battery, and this is given by the output RF power you get divided by the DC bias that you are applying into 1 minus 1 by gain. So improving the power added efficiency, it basically tells you in a way this is basically nothing but the output power of RF minus the input power of RF divided by the power DC. This is precisely what it means. Okay, this is precisely what it means, and this basically means that how efficiently are you converting the RF power. Okay, the output minus input. Okay, so you are subtracting out the input power, it takes into account the input that you are supplying. So power added efficiency is a very important number. You can see the power efficiency is not very high here, 28%, 25%, 22%. It can go to 50, 60, 70, 80% also, by the way, and those are really good for handheld devices for instance. So power added efficiency depends on gain, it also depends on this ratio. This ratio is called the drain efficiency, that is the output RF power divided by DC bias, the power and the DC bias. The power and the DC bias is constant, you are biasing at a certain question point, Q point. Say I am biasing at 0.5 amp and I am biasing at 28 volt of bias. In this case this was 10 volt bias, this is 8 volt bias, this is 6 volt. So say 8 volt at the drain bias and 0.5 amps is my biasing current. So this DC power is kind of fixed. Now the efficiency will increase, of course this drain efficiency will increase when your output power is increasing, correct. So your output power because the output power is numerator has to increase, denominator is constant. So the output power will increase when your input power increases, because the gain is linear, the gain is constant initially. So as you increase the input power, as you go along this direction, as you increase the input power, your output power increases because the gain is constant. So this is your output power. I will remove the annotation again here. You can see that your output power is increasing, correct. Your output power is increasing, as you are increasing the input power. Because the output power is increasing and the DC power is constant, it means your P output by RF power divided by P DC, this keeps increasing as you increase the input power, and that is why if this increases then 1 minus 1 by G, G is constant, you see in this part G is constant, the green one, right, the gain is constant. So this quantity, because the numerator is increasing, this is PAE, this will also increase, and that is why the PAE increases. You see this is a PAE, this is a PAE. A PAE will saturate when your output power saturates, or when your gain starts decreasing, then it will saturate. So in other words, the power added efficiency depends on this input, how much input power you can give, but how much input power you can give also depend on the device. If you are comparing a gallium arsenide MESFET versus a gallium arsenide HEMT versus a gallium nitride HEMT, to do an apple to apple comparison you need to have the same, say DC bias, say I am biasing it at 28 volt, I am having the same current of say 1 amp, you have to have the same kind of a bias condition, I mean say the same bias voltage, biasing current, and then you can make a fair comparison of the power added efficiency, because this will depend significantly on so many factors. Okay, but power added efficiency, it also depends on the biasing class, whether you are biasing in class A, class B, etc. also significantly affects that we are not going to discuss right now. But I told you, right, if you put the biasing point close to the pinch off where your waveform is clipped, then you are going to higher classes of operation. So in a nutshell, power added efficiency is a very crucial parameter for handheld devices, and it is directly depend on the gain as well as on the drain efficiency. Okay. So with this we come to a conclusion of the gallium arsenide MESFET discussion, where we talked about primarily on how gallium arsenide MESFETs are useful for power amplifiers, what are the important device metrics and parameters to keep in mind and how to improve that. Okay. So, thank you for your time, and we will meet you again in lecture 21 next week, while we start the discussion on modulation doping or HEMTs. Thank you.